Quantum mechanics is probably the most comprehensive and successful theory in all of physics. It's the deepest theory we have, with a truly uncanny power to predict correctly the results of measurements on atomic and molecular systems. And yet, as you've seen, it contains unsettling challenges to our most deep-rooted assumptions about the way the world works. In this program, we're going to examine some predictions of quantum mechanics that are almost beyond belief, and then put them to direct experimental test. To do that, we shall study a particular property of photons called polarization. Polarization is the property that allows a photon either to pass through a piece of Polaroid or be blocked by it. Passing through or being blocked can be thought of as two possible outcomes of a measurement of polarization of a photon. But instead of using a Polaroid as a measuring device, I can use this small cube called a beam splitter. It consists of two polished prisms of a material called calcite stuck together. You can see the line where the two faces meet. And what this device does is to give two positive and distinct outcomes for a measurement of polarization of a photon. I can put the cube in the path of this laser beam. It gives us spots on these two screens. Some photons are getting through, and some are being reflected. But every photon that gets through has vertical polarization. Horizontal extinction means vertical polarization. And every photon reflected by the cube is horizontally polarized. It's being extinguished by a vertical Polaroid. Now, I can introduce this Polaroid into the path of the beam. So the photons are polarized in the direction of the pointer. That's vertically at the moment. And as you see, the cube now passes all the photons straight through. The spot on the other screen has vanished. The cube is confirming that the photons have been prepared by the Polaroid in a state of vertical polarization. If I now rotate the preparing Polaroid to its horizontal position, to prepare horizontally polarized photons, we see the reverse. Only a spot on this screen here, and nothing on the first screen. And for intermediate angles, we get some output in both channels. For an individual photon, the two possibilities, going straight through with vertical polarization or coming out here with horizontal polarization, constitute a measurement with two possible outcomes. Many features of this polarization measurement are similar to the measurement of one component of spin of a spin-half particle. For example, the result of the measurement is only certain if the input state is one of the eigenstates of the observable measured, in this case, a state of horizontal or vertical polarization. Otherwise, some particles end up in one eigenstate, others in the other. And just as components of spin in different directions can be measured, we can measure the polarization at different angles by rotating the beam-splitting cube, like this. To each angle corresponds a different observable with two possible outcomes. Now, two devices, just like that cube, are at the heart of an experiment which reveals some of the deepest mysteries of quantum mechanics. And here is a model of that experiment. In the center is a source that produces pairs of photons that travel in opposite directions to one another. They travel down these tubes and into the analyzing cubes here and here. Each photon either passes straight through and is detected here, or is reflected and is detected here by sensitive photomultipliers. The measurement yields either vertical or horizontal polarization. Now, the essence of the experiment is to compare the result of the polarization measurement on a photon at this end with the result of a measurement on its companion photon made at the same instant at the other end of the apparatus. Well, It sounds very straightforward, but if we're careful about our choice of source, quantum mechanics made some very strange predictions about how this system will behave. In discussing the source, let's use an analogy from the discussion of spin in connection with the helium atom in Unit 15. Helium atoms have 2 electrons, and in a particular state, the spin state of the electrons can be represented by this state vector. Now suppose the source produces pairs of photons in the state represented by a similar superposition. As usual in quantum mechanics, that state vector will not predict the result we'd get if we make a measurement of the polarization on one of the photons. But what it does predict is this. If the 2 beam splitters are set at the same angle, whatever result we get for one photon, we should get the same for the other one of the pair. There's a perfect correlation between the 2 results. If one photon goes straight through, then the other goes straight through. If one's reflected by the cube, then so is the other, even though they don't have any definite polarization until a measurement is made. So these measurements are non-local. They depend not just on the photon and the detector here, but on the other measurement over there, even when it's made simultaneously. It was Albert Einstein, in collaboration with Boris Podolsky and Nathan Rosen, who first brought these strange predictions to the attention of the physics community in 1935. The predicted correlations, they argued, showed that quantum mechanics could not be a complete description of atomic phenomena. The instantaneous action at a distance, implied by these perfect correlations, seems to be at odds with the assumption of relativity that no causal influence can be transmitted at a speed faster than that of light. Einstein even went so far as to call these quantum mechanical predictions ghostly actions at a distance. Quantum mechanics contains no mechanism that explains in physical terms why the results at each end of this experiment are correlated. But Einstein felt that if the correlations exist, some such explanatory mechanism must also exist. Well, let's assume there is some mechanism. For example, perhaps there is an extra property carried by the photons that determines what the result of the polarization measurements will be. Each pair of photons emerges from the source with a particular value of this extra property, called a hidden variable, and this leads to correlated measurements at either end. The idea that the measurement of a photon simply reveals the properties that the photon possessed prior to measurement is an example of a common scientific assumption called realism. According to realism, the photon exists, independent of any measuring apparatus. And when we measure it, we reveal the properties that it already possesses. We don't impose the properties on it by an act of measuring it. The lack of predictability in an individual measurement comes from the lack of control over the value of the hidden variable that any pair of photons has as it emerges from the source. The idea of hidden variables would eliminate non-locality and restore realism to the physical world for 2 reasons. First, the result of a measurement at each end is determined by the particular value of the hidden variable of the photon at that end, not by the result of a simultaneous measurement made somewhere else. That's locality. Second, the photon has a definite value of the hidden variable prior to measurement, and the measurement only reveals it. That's realism. Now, it is the case that theories using hidden variables have been devised that can account for the perfect correlations that result from 2 detectors set at the same angle. So any experiment depending on just perfect correlations wouldn't force us to choose between the quantum mechanical explanation and a hidden variable theory. But it was John Bell, a physicist now working at CERN in Geneva, who first showed how to bring these 2 forms of theory into direct conflict so that experiment can decide between them.
I think there is no puzzle so long as your 2 analyzers are parallel to one another and you have perfect correlations or perfect anti-correlations. The fact that a yes on one side implies a yes on the other side is no more mysterious than the fact that if you look at one of my socks and see it blue, there's an extremely good chance that the other sock is also blue. So correlations like that are not a puzzle, provided you admit the socks are really there before you look at them. It's a mystery if looking at one sock makes it blue, makes the other one blue at the same time. So Einstein's way of looking at the Einstein-Podolsky-Rosen correlations seemed to me very natural. There is something there even before you look, and it's correlated on the two sides. Nevertheless, there is a puzzle, and the puzzle comes not with the perfect correlations, but with the imperfect correlations which occur when your polarizers are not quite parallel.
The imperfect correlations correspond to an arrangement like this, with the analyzer at one end set at an angle theta to the analyzer at the other. Otherwise, the experiment is exactly as it was before. But now, there are four possible outcomes: vertical-vertical, horizontal-horizontal, vertical-horizontal, and horizontal-vertical. Now, we can use quantum mechanics to predict how many of the four possible combinations of events will occur as a function of theta, the angle between the two polarization detectors. It's done in the notes. Those predicted results can be used to produce a particular function, s of theta, that looks like this. What John Bell did was to show that for any local hidden variable theory, the graph of this function, s of theta, would never fall within this shaded region. That is, it would always lie between plus and minus 2. This is the so-called Bell inequality, a precise theoretical conflict between quantum mechanics and local realism. Well, I've said so far, let's suppose we can make a source of correlated photons and detectors sensitive enough to test these strange predictions of quantum mechanics. For Einstein and his colleagues, this was a thought experiment which challenged the most basic assumptions of the nature of the real world. But 50 years later, by the 1980s, technology had advanced far enough for it to be put to a decisive experimental test. And it was here at the optics laboratory in Orsay, France, that the experimenters Alain Aspect, Philippe Grangier, and Gérard Roger worked for years to develop the source and detecting equipment that would make such an experiment possible. And this is the lab where the crucial experiment was done. The basic elements of the experiment are a good source of correlated photons, that's this here, and two detectors separated by 12 meters to measure the polarizations of the two photons. An ingenious feature of the source are these laser beams. There's one that goes in through here, another goes through a port on the other side. They both, together, excite the calcium atoms that are contained in the vacuum chamber. An oven, like this, situated at the base of the chamber, creates a very fine beam of calcium atoms that rises up through the vacuum chamber. The simultaneous excitation by the two lasers causes the calcium atom to rise from the ground state to an excited state. From there, it decays by a two-step process that produces two photons, one of which goes 6 meters down this tube to the detector down there, and the other goes 6 meters in that direction to a corresponding detector. Both the detectors and the source were specially designed by Alain Aspect and his co-workers to make this experiment a precise and very clear test of quantum mechanical predictions.
The principle of the source is to emit a pair of photons correlated in polarization. And the scheme of levels that we have selected is this scheme of level in the calcium atom. And if you are able to excite a calcium atom in this level, then it will decay, emitting a first green photon, new one, and then a second violet photon, new two. And these two photons are correct candidates for a test of Bell's inequalities. Now the question is how to excite the atom to this upper level. Suppose you shine a laser on this atom, then you can have the atom in what we call a virtual state. If during this extremely short time you are able to send a second photon with the correct energy to reach exactly this upper level, then the atom will be excited to this level. And once it is in this level, the atom has no choice. The only thing it can do for you is just decay giving the right cascade.
The technological breakthrough that made it possible to construct such a source was the development of tunable lasers. With these lasers, intense beams of the exact total energy could be focused on the calcium atoms to produce an adequate number of pairs of photons to be measured by the detectors.
I'm at the detecting apparatus at one end of the experiment. Let's have a closer look at the cube. You can see the diagonal face that separates the two states of polarization.
Both the transmitted photons and the reflected photons are detected by photomultipliers, especially designed to deliver an electrical pulse on the arrival of each single photon.
The photons that go straight through are collected in this photomultiplier here. But the photons that were reflected at 90 degrees would have been collected in another photomultiplier that was screwed into this hole. We've taken it out in order to let you have a look at the cube. And this whole apparatus, that is the cube and the two photomultipliers, can be rotated as a unit in order to have any given selected angle with respect to a similar detection apparatus at the other end of the experiment. But the essence of this experiment is really the correlation of the counts that are registered in this photomultiplier with counts that are registered in the photomultipliers at the other end of the apparatus.
The correlations between polarization measurements at either end cannot invoke any known mechanism as an explanation.
So, which theory do the experimental results support? Quantum theory or a local hidden variable theory? The conflict between these two theories is demonstrated by the function S of theta. The quantum mechanical prediction for S of theta clearly takes values in these regions that are forbidden to any local hidden variable theory. And what does experiment say? Have a look. Each experimental point is the result of detecting approximately 8,000 pairs of photons. The confirmation of quantum mechanics and the rejection of hidden variable theories is stunning.
But truly, how isolated are the two ends of this apparatus? One nagging possibility that really should be eliminated is this. In a given run, the angle between the two polarizers is set, and then it's held constant while all the measurements are taken. Now, is it possible that the two detectors can communicate to the source that angle so that the photons that come out have the right properties so that the quantum mechanical results will be obtained for that given angle? And with every given angle, the appropriate signal goes from the detectors to the source so that quantum mechanics is always obeyed. Now, no matter how far-fetched that idea might seem to you, this experiment, as we have looked at it, cannot decisively deny that possibility. True isolation has not yet been achieved. Now, one way to do it is to put two detectors at each end of the apparatus and set them at different angles, and then cause the apparatus to select one of the two detectors so quickly that the resulting angle between a detector at one end and a detector at the other end is chosen after a photon has left the source and before it arrives at the detector. So the detector cannot influence the source in the way I've described. But in order to do that, we would have to be able to switch the beam between the two detectors at one end within a 20 nanosecond period. That's the time of flight from the source to a detector. And this is the lovely piece of experimental equipment, the switch, that will do the job.
The device is a container with windows on either side. Acoustic transducers in the top and bottom, driven at 25 megahertz, set up a standing wave of sound in a liquid that is held in the container.
Same time, the acoustic wave has nodes and antinodes, and then a quarter of period of acoustical period later, there is nothing else. And then a quarter of period later, again, something like that. That is to say that sometimes there's a grating, and so the light goes into the first order of diffraction. A little later, there is no more grating. It's just a piece of transparent material, and the light goes through. And then a little later, again, the grating is here, and it goes here, and so on. And the fun of the thing is that after searching for all sorts of very complicated materials, we eventually found that water was the best material suited for our purpose. So we have built this system just with water.
Even with the switch in place, the agreement between experiment and quantum mechanical prediction is impressive. If we plot the probability of getting two vertical results as a function of the angle between the polarizers, quantum mechanics predicts this curve. And here are the experimental results obtained with the switch in operation. Using these data to test Bell's inequality leads to the result that there is only one chance in 10 to the 10 that Bell's limit on S of theta could be consistent with this experiment. So, here's where we've arrived. 50 years ago, Einstein, Podolsky, and Rosen made it clear that quantum mechanics predicts the existence of correlations of simultaneous measurements over arbitrary distances, not just the size of the atom, but the scale of a laboratory, or bigger. Since they couldn't believe in instantaneous correlations, they concluded that quantum mechanics is not the ultimate description of the physical world. One way to restore locality is to introduce extra variables into atomic systems to account for the correlations. But 30 years later, John Bell's work enabled experiments to be designed which could decide between local hidden variable theories and quantum mechanics as a theory of physical processes. Now, Alain Aspec's experiments have decisively vindicated quantum mechanics. There really is ghostly action at a distance in nature. But while quantum mechanics predicts these effects, it gives us no way to understand, in physical terms of cause and effect, how these correlations come about. So, in quantum mechanics, we have a theory that gives us an amazing power to predict correctly the results of experiments on atomic systems while leaving us totally unable to visualize how some of these atomic processes occur.
Well, we've got to take the world as it is given to us and live with it. And in fact, as you know, physicists have for 60 years or so worked extremely successfully with this situation. The formalism of quantum mechanics, using it in the way that we know how to use it, has been fantastically successful, and it shows no sign of running out. I want to make that clear, that the conventional developments that I most of the time and most of my colleagues all of the time are devoted to are extremely impressive. So it is a very intriguing situation that at the foundation of all that impressive success, there are these great doubts.